Morning guys, welcome back. So yesterday we started looking at manipulating and solving through formulas. Yes, you will always have a formula sheet for any quiz and test. We just want to make sure when given a formula, when given a relationship between many different variables, I can do the evaluate it, I can isolate for certain letters, and then I can punch in the numbers to actually evaluate my formula. So let's just do one quick practice question there, and then today we're going to introduce to you quadratic formula as well as a little bit of trigonometry towards the end. Just for a quick warm-up here, again, I encourage you to actually do this in your notebook. After you copy down the question, just pause the video, try it out for yourself, see how you do, and then you can unpause and check your answer. So just for a quick warm-up here, I'm going to give you the expression. So this would be sort of like looking on your formula sheet here, looking for the relationship between some of these variables. We're going to come back in our first big chapter of kinematics to actually look at more of the understanding of this here. In this case here, we're going to start off with a situation. An object is dropped from rest. Rest means it's not moving at the beginning, and accelerates it's going to be gravity that's actually pulling the object downwards. We're going to come back later on to actually do it more precisely at 9.8. In this case here, I'm just going to round it to 10 meters per second squared. And it's going to be dropped for 3 seconds. I want you to calculate the distance, the d, traveled. Okay, so again, if you can just sort of draw a picture to this one here, all the better. We're starting with an object, it's being dropped, so I'm imagining this object here is somewhat higher up. We're told that it starts from rest. Rest is another name from saying that the initial speed is actually 0. I'm holding on to it until you say go. When you say go, I just drop it. It then accelerates at 10 meters per second squared. Again, we're starting to see more familiar with this. Anything that's measured in a meter per second squared is actually an acceleration. So in this case here, we actually put in the acceleration of 10. This means, again, just translate it for yourself, we increase 10 meters per second speed faster each second. So after 1 second, you're 10 meters per second faster than you were to begin with. So let me just draw a quick picture of this one here. Let's say at 0 seconds, I say go, you can drop the rock. At 1 second, it would now be traveling downwards at 10 meters per second. Right? Gravity pulls things towards the center. So we have 10 meters per second here. At 2 seconds, it's actually going to fall a little bit farther, but we can actually know it's going to be 20 meters per second. Now, what I want to introduce to you here is acceleration is actually a constant. So it's not going to be like for the first 0.9 seconds or so, we're just at rest. And then suddenly when we hit 1 second, we hit a 10. It actually gradually increases over time. We're going to be, traveling at 2 meters per second, traveling maybe 6 meters per second. We will eventually speed up. It's just by 1 second, I'm going to be 10. Then I'm going to be traveling maybe 12 meters per second, 15 meters per second. By 2 seconds, I'm going to be 20 meters per second. It's just going to constantly be increasing. It's just my acceleration just sort of samples it at, for every second, you are 10 meters per second faster than you were to begin with. This one here should be intuitive to you here. You will notice that the distance in the first time interval is actually a little bit less than the distance in the second time interval. I may similarly be changing by my speed goes up by 10 meters per second. This one also goes up by 10, but going from 0 to 10, right, if my speeds are only like 2 meters per second, 3 meters per second, I'm not going to actually travel that much distance. At 1 second, I'm already going 10 meters per second. Even if you give me just 1 second without speeding up, I already have gone 10 meters per second. For 1 second, I've gone 10 meters. And let alone here, my speed is actually increasing. Now I'm going 12 meters per second or 14 meters per second here. In this same 1 second time interval, because the magnitude, the size of the velocity was so much higher, I'm actually going to travel much farther in the second than the first second. So I need to weigh out all that here as I do my formula. What's measured in seconds here is going to be a time. I want to look for a formula on formula sheet that I have all the variables except for one unknown. In this case here, it was a new formula. I haven't given you this one yet, but you can probably guess here. The distance here is actually given by d. I want to know the total distance, sort of compensating for, well, which I start out just not traveling that fast and not traveling that far, and then I travel farther. If I do this for 3 seconds at a time, what is my overall distance? What's really helpful in this section here is if you can make a list of your variables. So far I have vi is equal to 0. We were at rest. I have my acceleration, which is 10 meters per second squared, and I have my a, which is 3, I'm just sort of keeping a running list so that wherever I see these letters, I can punch in these corresponding numbers. As always, even if I have my formula, I would write out my formula just to make sure I'm going to manipulate them properly. So d is equal to VIT plus 1/2 AT squared. I am looking for d, and it's actually already solved for d, so which is even nicer. And all I'm going to do is I'm going to punch in the other numbers. So in this case here, my VI is 0, my time is equal to 3, plus 1/2, my acceleration is 10, multiplied by t again. In this formula here, be careful, again, this is the first time we're seeing this formula, but it's only the time that's being squared, the rest of it's just being multiplied, so it's 3 squared first, and then multiply 10, multiply half. So crunch through all those numbers here. 0 times anything just gives you 0, so that part just sort of dies away. We're going to get 0.5 times 10 times 3 squared. It gives us an overall distance of 45 meters. So sort of considering at first I don't really go that far. If I do this for 3 whole seconds of speeding up, I actually travel a total distance of 45 meters. That's how far it actually falls. Later on, when we actually do this in kinematics, we're actually going to use acceleration. Because this rock here is actually falling downwards, later on we're going to do an acceleration as, let's say, negative 9.8. We're going to see as fairly sloppy sort of, let's add a negative or let's take away a negative. The negative just indicates to you direction. So either you just have the negative in the number or you just write in words. Because I know gravity pulls things downwards, I know I'm going to now be 45 meters down or lower than my starting position. So hopefully through the worksheet you got some practice with that there. The next part of our sort of math toolkit review here is I want to recap with you quadratic formula. There's about 2 or 3 times in this course that we'll actually run into a quadratic formula. So I just want to introduce to you, when we have a quadratic formula here, how do we solve through the math so that we can make it a little easier for future. So let's start off here. This is called the quadratic formula. My guess is some of you have seen this formula before. I even give you the formula on the formula sheet. The formula is written here if you have something formatted here, if ax squared plus bx plus c is equal to 0. They've actually done the isolating for you. Imagine trying to do it yourself. Imagine trying to solve for an x. Well, if it's not x, you want to kick it over the other side. You can kick the c over no problem, but then you're going to have a problem. Well, what do I do with one that's a squared, one that's not? You can try to square root. Maybe you can get rid of this x squared, but then I'm going to get a root x. It's not going to be really easy to solve. This is why they just gave it to you as a formula here. If you have this expression listed in this fashion, all we actually need to know is the a, b, and c. They've done the math for us, and they've actually figured out here then the x is equal to, this expression is a little bit scary. We're going to take the negative of b. We're going to flip the sign of whatever the b constant is. We're going to plus and minus. There's going to be a square root. Underneath the square root, this is called the discriminant. We get a b squared minus 4ac all over 2a. And again, the challenging bit here is not, can you memorize the formula? This will be provided for you on the formula sheet. All I want you to practice today is just punching in the numbers as is. So they've actually done the isolating for you. When it would have been really hard to do our own solving, they've actually given you the expression. And all we really need to know is the constants. What's the constant for the squared term? What's the constant to the power 1 term? And what's the constant which actually has no variable to it? So let's just practice through a quick question here. Let's start off with, we have 2x squared plus 5x minus 3 is equal to 0. Right? So what I want to do in this case here, I just want to match it up to my formula. I want to make sure it's the same expression. In this case here, a was my squared term. That means in this case here, a is equal to 2. Right? So when I punch into my quadratic formula, I'm going to put in 2 for a. B is actually equal to 5, because that's going to be the constant here. What would c equal to? Now you'll notice in my generic formula here, it's actually expressed as a plus c. In this case here, when I actually have my number, it's actually a minus 3. You can think of this actually a plus, a negative 3. So therefore, the c term that I'm going to actually punch in, c by itself actually hides a negative. So when I plug that into our c in the expression, that's actually going to go in as a negative. That's actually all you need to know, the a, b, and c, and then we can just use a quadratic formula. There's a little bit more math here, so let's just copy it out here. Negative b plus or minus the root of b squared minus 4ac all over 2a. All I would do is I would just punch in the numbers as we're used to. If I take the negative of b, b was just equal to 5. plus or minus the square root, there's b again, so I'm going to take 5, this time they want you to take b and square it. Then comes a minus 4 times a times c, so minus 4 times my a was equal to 2, and my c, like I mentioned, is actually a negative 3. That's important there, because times 3 and times negative 3 are different. And then this is going to be all over 2 times the a, and a is, again, equal to 2. So first thing we say, well, in this expression here, I can solve it because I don't have any more unknowns. Somehow, by sort of manipulating through all these number crunching here, I can end up getting what the x's are going to be. So let's just clear up some of the terms at the top here. I generally like to type in this sort of the bottom part, deal with what's underneath the root first. So this is negative 5 plus or minus 5 squared is 25. I'm going to minus 25 minus 4 times 2 times a negative 3. This gives you a nice root 49. 2 times 2 is equal to 4. We're going to find later on in this course here, these ones here might end up as decimals. Underneath the square root here might not be a nice number, but mathematically, though, we are taking the square root of this. In earlier math classes, you may have learned to do a factoring style. Let's find two numbers that multiply to give a times c. Let's add it to give this one. That works nice when things are nice, easy whole numbers and we're sort of guessing and checking. The second I make this a decimal, like 2.7 or 3.12, then it becomes really hard. The quadratic formula here still works. So let's just punch our way through the math here. X is therefore equal to negative 5. There's this funny plus or minus that we'll deal with in the next step here. So root of 49 is equal to 7. In fact, what this plus or minus deals with, it's actually a nice shortcut. At this point here, I need to sort of separate my plus and minus. One of them takes the plus root, the other takes the minus root. Now, one thing I want to caution you here is it doesn't mean your answers, first thing is there's two answers, but it doesn't mean your answers, one of them has to be positive, one has to be negative. The only part that's sort of one side plus one side negative is actually just in this formula. So one of your answers, let's call it x1. x1 is going to be negative 5 plus 7 over 4. It takes the plus of that plus minus sign. My x2, which is the other solution, is negative 5. I'm going to actually do a minus 7 divided by 4. So to separate that plus and minus, one side takes it with a positive, one side takes it as a negative. Depending on what the actual numbers actually were, maybe your x still ends up positive or maybe it still ends up negative. I don't really know that. In this case here, I think I get one of each. So let's try it out here. Minus 5 plus 7 is equal to 2. 2 over 4 is equal to 0.5. So 0.5 is one of your answers. Negative 5 minus 7 is equal to negative 12. Divided by 4 now gives you negative 3. Again, the quadratic formula here should give you two formulas. If you want to do this in sort of your math class here, we know when we have an x squared, we know we're dealing with a parabola-like shape. And basically what's happening here is I'm saying, where does your function, where does your parabola actually run into the x-axis? Where is that equal to 0? Right, that's what your quadratic formula says. Where does your parabola actually run into 0? This one here would be sort of like your y-intercept. X-intercepts. Is where does it run into the graph there? And so far we have the x-intercept here. When x is equal to negative 3, it solves the parabola. When x is equal to 0.5, it also solves the parabola. We have two answers to the problem. It's totally possible that sometimes, based on my numbers I give you in the quadratic, maybe I should scale this over a little bit. Okay, I know it's not exactly symmetrical. Maybe something more like that. It's possible that your parabola may be upside down. It's possible that your parabola may not even run into the x-axis at all. It's possible your parabola might only touch once. But basically, the quadratic formula, even if the numbers get to be a little bit scarier, it still ends up giving you the right expression. So I'll let you practice through one here. So just more quadratic here. Let's take a t squared minus a 6t is equal to negative 5. I want you to solve for t. Right? So this looks like a lot like your yesterday's lesson here. Solve means solve your way, isolate your way so as t equals something. Again, because this is a slightly harder problem, it's not so easy to deal with the t's. Because I have one t that's being squared, the other t actually has no power. I can't kick it over there because I want to collect all the t terms together. And yet if I try to, let's say, square root this side here, you might end up with a root t somewhere along the way. It's not going to be really easily. So just showing you, again, it's sometimes not easier to actually solve for. However, because we recognize this, when I have something that's squared, when I have something that's powered, I'm going to try to match it up to this sort of formula here. I'm going to try to get it to an ax squared bx plus c equals 0. Kick everything over to the left side so that we actually have a 0 on the far side. So in this case here, I'm just going to bring the negative 5 over. I'm going to go t squared minus 6t. I'm going to add the 5 over, and now it's equal to 0. Now we have an exact match of my quadratic formula, and now I just need to find my a, b, and c, and therefore we're done. So my a here, well, even though they don't show it to me, I know a has to be 1 times t squared. My b would actually be the negative 6, right? So careful of that negative there. This time my c is positive, fine. Those are only the 3 constants that I need to solve this quadratic formula. Now it's just for you to practice doing the quadratic formula. So this time they use the letter t. Ooh, big difference. Negative b plus or minus the root of b squared minus 4ac divided by 2a. I'm going to punch through my numbers here. You could, again, solve this by factoring. I kept the numbers fairly easy, but I just wanted you to practice through using the quadratic formula. As I just punch my way through my numbers, I just plugged in my a, b, and c. You'll notice I put them in brackets so that, again, when I just match it up, if I make a mistake later on, I can see what math I did. So b itself was a negative. I'm going to take a negative and negative, so that becomes a positive. When I take b squared, just careful how you type this in your calculator. It is going to be a negative 6 squared. If in your calculator you just type negative 6 squared, the calculator doesn't understand that. What the calculator would do there is it says, okay, square is more important. It's going to take 6 squared, it's going to do a 36, and then add the negative afterwards. Is that what I want? Well, no. In this case here, I actually want the negative 6 to be in the brackets. When two negative numbers multiply together, it should actually be a positive number. In that case there, you actually need in your calculator, put the bracket around the negative 6, tell the calculator, nope, it's the negative 6 that's being multiplied by another negative 6, and it should actually give you a positive 36 instead. So let's just try our way through here. Negative and negative 6 becomes 6, plus or minus negative 6 squared should be a 36, minus 4 times 5. Again, I kept the numbers fairly simple, divided by 2. Underneath the square root, again, there's a really nice number, square root of 16 divided by 2. It's a nice even root there. We know the root of 16 is equal to 4. Yes, I can get a plus minus 4. That's sort of what's taken care of by this plus minus here. At this point here, this is sort of, that's as simple as I can get this. And now what I'm going to do is I'm going to get one of the answers taking the positive answer, one of the answers taking the negative root. This time my letter is t, so be it. T is equal to 6 plus 4 divided by 2. That takes the positive part. My t2 is equal to 6 minus 4 divided by 2. And therefore, when we look at our answer here, 6 plus 4 is equal to 10 divided by 2. The t could be equal to 5. Or the t could be 6 minus 4, which is 2 divided by 2 is equal to 1. Again, our parabola ran into the x-axis twice. I just wanted to show you an example. Notice both my answers are positive, so be it. That's fine, right? It's just when I did the operations, one took the positive side, one took the negative side. So make sure you're comfortable using the quadratic formula here. We're going to review one more thing in today's lesson, which is a little bit of trigonometry. We're going to see a lot of triangle practice in this course. So again, I just want to introduce to you some of the math around that. So just a quick recap of trigonometry. So looking at triangles, specifically the triangles that we're going to be dealing with here are going to be right triangles. If you've done a sort of further studies in geometry, you may have done cosine law, sine law, things like that. We're just going to simplify things a little bit, and we're just going to look at a right triangle, which means it is a triangle that has a right angle in it. Right angle you can sort of denote with this sort of square symbol here. That square there just means it's a 90-degree angle. So what I'm going to give you here is 4 right triangles here. There's a couple things I can measure. I can measure for you angles, so how many degrees. So in this case here, let's say it's a 30-degree angle. It could have been anywhere between, let's say, 0 and 90. In this case here, if I give you this angle, there's a couple names for the different sides that we have. The side that everyone knows here is the hypotenuse. The hypotenuse here is going to be the longest side. Hypotenuse is always going to be across from the 90-degree angle. It's always the longest side. That's your hypotenuse. Don't know if I spelled that right here. Hypotenuse. Depending on the angle, however, we give a name to the other two sides here. If I imagine the angle here to be an eyeball, the side that the eyeball is actually looking at is actually going to be called the opposite. Right? That's opposite the angle. The side that's beside you, the side that's sort of adjacent, the side that's sort of measuring with the hypotenuse, this bottom side here is actually called the adjacent. And what you're going to find is, depending on the angle that they give you, the hypotenuse is not going to change. Hypotenuse is going to be the longest side. However, if I give you the other angle instead, let's say I give you this top angle, if my eyeball is now sitting over here, now what used to be adjacent is now actually the opposite side. This side here is the adjacent at this angle. Opposite and adjacent might switch depending on what which angle you're actually labeling. There's a couple formulas we can deal with for a right triangle. First type of formula here is called Pythagoras, or Pythagorean theorem. Pythagoras essentially says here, a squared plus b squared is equal to c squared. So the only thing you need to note in this formula here, the a and the b are the legs of the triangle, are the shorter sides. C has to be the hypotenuse, C has to be the longest side. In that case there, it really doesn't matter which you call A, which you call B. Right? In fact, we're going to do this so much so that I'm actually going to solve for C. If I want to just get C in this relationship, all I'm going to have here is I'm going to go C is equal to the square root of a squared plus b squared. That's going to be a nice shortcut for you later on. It's still the same Pythagoras formula, but slightly rearranged just for C. That's sort of our first formula with this right triangle here. The other type of formula for this one here are your trigonometric functions. The trigonometric functions here for just memory aid here, we usually say SOHCAHTOA. Right, so the three functions are sine, cos, and tan. And basically what this sort of mnemonic memory aid here tells you is it actually gives you what are these operations, what are they ratios of. So in this case here, let's take S, which is the sine function. So sine, careful when you do these operations here, the trigonometry functions are applied on an angle. The letter I'm going to use for an angle is actually the Greek letter theta. So sine of my angle is equal to OH, and that's actually going to give you opposite of hypotenuse. So sine of anything, so let's say sine of this angle theta, theta is my angle. If I take sine of 30, that's automatically going to give me the ratio between how long the opposite side is divided by my hypotenuse. It's going to give me that fraction there. What the other trig functions do is they actually just play around with which legs that we're comparing. Let's say cosine, cosine of theta. Again, whenever you do the operation, it is operating on a degrees. Cosine of theta, because it's a and then h, it actually gives you a link between adjacent over hypotenuse. And finally, we have tan of theta, tangent of theta is O over A, which is opposite over adjacent. So we have three trig functions here that interrelate the different sides on the triangle here. Let's see how this works out here. Let's start off with a triangle here. Let's start off with a 40-degree angle. Right? Just make things a little bit different here. I'm going to give you the hypotenuse. Let's say the hypotenuse is 50. I'm interested in you calculating what's the x and what's the y. Usually x is horizontal, so it's okay for me to label that there, and we have the y. What I want to do here is I just want to label the different sides. So just like the triangle we just did here, we know we have a right angle triangle. We know the one that's across from the triangle. We know this side is the longest side. That's called the hypotenuse. I could try using Pythagoras, right? X squared plus y squared is equal to 50 squared. Oh, I can't do it right now because I have two unknowns in the problem. I need to use the other unknown. The other thing that they give me in this question here is actually the theta. And what I want to figure out is which of these functions can I actually use. When you use a formula and you're finding a variable here, you have more freedom to find the next variable. So for example, if I was looking for x, which side would the x be? If this is my eyeball here and the eyeball is looking across, that's opposite. So x is actually going to be the adjacent. I'm looking between sine, cos, and tan for the one that actually tells you the relationship between adjacent. The one that has adjacent and hypotenuse, oh, that's just cosine. So I'm going to rewrite the formula here. Cosine of theta is equal to adjacent over hypotenuse. Cosine, let me actually give you that word there. This circle with a letter, with a line through it here, this is the Greek letter theta, usually an angle. So cosine of my angle, which is 40 degrees. The adjacent I don't know, but I put a placeholder in for x, and I'm going to divide it by the hypotenuse, which is 50. If you have never seen this here, I know the cosine of this theta here looks a little scary. All you're going to do is you're going to punch that in the calculator. Cos 40 is going to give you some decimal, and then we can just bring the 50 up, and we're all good. In fact, I want you to be able to just really shorthand say, well, x is adjacent. X is going to be the hypotenuse. Cosine of 40, essentially we just took that 50 up. At this point, make sure you put your calculator in the degree mode. Especially graphing calculators, their default as radian mode. That's convenient for calculus, but not so much for physics here. Let's go 50 cos 40 in degree modes. This gives us something less than 50 as we would expect. We'll worry about the rounding in a later lesson here. That gives you the ballpark of about 38 or so. At this point, you actually have more information. I now know the x is actually going to be what we found was 38. Because I now have two sides, I could actually punch it into Pythagoras. So I could actually go 38 squared plus y squared has to equal to 50 squared, rearrange that to solve for y. If I had the choice, however, just in case I got the x wrong, I don't want this number knocking off my other answer for y. So if I had a choice between many functions here, I might actually look to, is there a way for me to actually solve for y without actually relating to x? In this case here, if I use tangent, sure, I can do tangent of 40 is equal to y over x. Oh no, that relates to x as well. What if I use sine instead? Sine actually deals with the opposite side, it deals with the 40, it deals with the y, and it also only relates it with 50. In that case there, it should be a little bit easier. Just in case I got x wrong, I don't want it to knock y off. So let's use the sine function here. Let's go sine of theta. Sine of theta is supposed to be opposite over hypotenuse. That's where your SOHCAHTOA comes from. In this case, I'm going to take sine of my 40 again. This time, my opposite side, the side that my eyeball is looking at here, is going to be expressed as y divided by 50. Again, I want you to be comfortable. Well, y is going to be the opposite side, so 50 sine 40. And now I can just fully express it here. 50 sine 40 gives you 32. Right. One last note here is, especially we've just found the numbers, you can put them into Pythagoras. When you do 38 squared, if you punch in 32 squared here, it should give you give or take 50 squared, maybe give or take a little bit of rounding because I sort of truncated some of these decimals here. But those are our relationships here. Using the hypotenuse and the angle, I was able to find the two other numbers. You can even test it against tangent theta. Tangent theta should give you 32 over 38. One thing I wanted to remind you here is, in this case here for this triangle, remember angles in a triangle always add up to 90 degrees. I have 90 degrees, either this is 40. I actually know the other angle is 50. In this case here, if this one here is 50, the only difference, hypotenuse doesn't change. Hypotenuse is still my longest side. But in this case here, I'm going to say opposite is x, and then adjacent is equal to y. Opposite and adjacent are relative to which angle I label. So on your worksheet, you're going to get a little more practice with this one here. We'll pick it up from there tomorrow. Thanks, guys. Take care.